Our next speaker is Violeta Podanovic from Diego Instruments, and her paper is on artifact-free decapsulation with atmospheric plasma for all-bond wire. Violeta received her Master's of Science in Electrical Engineering from the University of Belgrade in 2013. In 2019, she obtained her PhD in the Electronic Components, Technology and Materials Group at Delft University of Technology, after conducting research on ultra-thin transmission diodes for a novel type of a timed photon counter. She joined Diego Instruments in 2020 as a sales engineer. Please welcome Violeta.
Hello, I'm not on mute anymore, right?
Correct. We hear you.
Okay. Thank you for the introduction. So as announced, I will be speaking today about artifact-free decapsulation with atmospheric plasma for all bond wire types. So my presentation will be structured as can be seen here. I will give a short introduction about the decapsulation method that we used, which is microwave induced plasma, or MIP. Then I will outline differences in results between acid and MIP, and also conventional plasma decapsulation and MIP. After that, some MIP case studies on different wire types will follow. So allow me to start with the short background and to give a short introduction about our company. Diego Instruments is a manufacturer of leading-edge atmospheric pressure microwave-induced plasma (MIP) decapsulation systems, which are being used in failure analysis and reliability testing of packaged ICs. A short history of our company. So in 2005, the fundamental research on the novel decapsulation process started, and the company was formed as a spin-off at Delft University of Technology after a PhD research in 2014. In 2015, we built our first beta machine, and first commercial machine followed in 2016. Until now, FA labs across the globe have been equipped with more than 45 MIP tools in total. Plasma source and plasma etching process have been designed, patented, and manufactured in the Netherlands. So, semiconductor devices are routinely decapsulated for failure analysis and quality control. In this FA flow, as you can see, decapsulation as a part of sample preparation is nested between non-destructive analysis and failure localization, which is usually different microscopy techniques. Decapsulation actually represents selective removal of the molding compound, which consists of 10% of the epoxy and around 90% of silica fillers. Due to the limited amount of samples and time pressure, reliable decapsulation is a prerequisite in field returns. Decapsulation requirement is the preservation of following elements: metal bond wires, bond pads, silicon dye, functionality data, and also original failure sites. All this is absolutely necessary so that reliable analysis is performed afterwards. Okay, this slide gives a comparison between results of MIP and acid. On the image right, we have a device which contains palladium-coated copper wire and has been decapsulated in cold acid. As you can see, the neck wire has been severely damaged by corrosion, and on the image on the left, you can see the same device decapsulated by microwave-induced plasma, where we can see that original surface has been preserved and no apparent damage on the bond pad, wire, and ball bonds have been observed. This slide outlines differences between MIP and conventional plasma systems. So the main difference is actually in the etching gases. Conventional plasma systems for decapsulation usually use mixture of CF4 and oxygen, and MIP is oxygen-only etching system. Due to chosen chemistry, MIP will not induce any damage and over-etch silicon or passivation layers such as silicon nitride, which conventional plasma decapsulation method will. Again, conventional plasma systems, conventional plasma decapsulation is a highly uncontrollable process with a low selectivity, and due to that, it is very difficult to implement endpoint detection. On the other hand, MIP process is just a gentle oxygen etching and does not require an endpoint detection. MIP will preserve electrical functionality of decapsulated devices, unlike conventional plasma. And another important difference is that MIP is a fully has a fully automated operation, in a sense that etching and cleaning steps are conducted automatically, as will be shown in a few slides. On the images here, there are results of devices which have been etched by MIP on the left, and by CF4 containing plasma, where we can see a nasty over-etching damage. Now, this is an anatomy of a microwave-induced plasma system. So the machine consists of a microwave generator, a microwave resonant cavity, which is custom built and of a Banneker type. Then there is a gas discharge tube, which is inserted through the center of the cavity to sustain the plasma. It is usually made of quartz or aluminum. Then we have mass flow controllers, a CCD camera, which enables real-time monitoring of the plasma etching process, a programmable stage so that the scanning routes can be customized, and there is a cleaning unit and a drying unit. MIP machine operates at atmospheric pressure, and this means that the mean free path of ions is extremely low, so that only long-lived oxygen radicals in plasma effluent will actually contribute to etching. In the MIP system, plasma beam is confined, and sample heating is directly through plasma effluent. So this is how MIP decapsulation process looks like. So the starting point is the sample preparation, which can be laser ablation or mechanical polishing. Next step, high density oxygen plasma is scanned across the device surface, and by this epoxy in the mold compound is selectively removed. So after oxygen MIP etching, silica filler particles in the compound are left on the surface, and they can be seen as this white agglomerate layer. Furthermore, device is then automatically transferred into ultrasonic bath with DI water, and the cleaning process will selectively remove silica fillers and expose a fresh layer of mold compound to be further etched. Device is then dried and then automatically transferred back for an etching step. These steps 1 and 2 are being repeated sequentially in cycles until the device is fully decapped. Now, this slide shows a unique capability of MIP technology in the decapsulation of copper wire bonded IC packages after thermal reliability testing. So after devices have undergone thermal testing, decapsulation is required in order to perform pull and shear tests. However, throughout thermal testing, the mold compound gets very hardened, and it is even more difficult to have it removed by acid. Removal of this mold compound requires then a longer immersion time in acid, which causes more damage to the wire bond pads. Due to this damage, wire pull test data obtained after acid decapsulation will be unreliable. As an example, we show here the decapsulation of an SOP package with 25 micron bare copper wire and high TG Sumitomo mold compound, which is used for encapsulation. Acid decapsulation on the left shows that copper bond wires have been dissolved due to corrosion. Image on the right is a result after MIP decapsulation, and SEM inspections of the ball bond and the copper wire shows no apparent degradation. To conclude, MIP decapsulation does not influence original wire condition and ensures reliable pull and shear data. On the next slide, I will talk about MIP decapsulation, decapsulation of packages with silver wires. So silver-based materials are actually inherently susceptible to etching damage by acid. For that reason, some of the following methods have been proposed to improve conventional acid decapsulation. So 2 out of these 3 presented methods actually provide sort of a barrier layer, which will then protect silver surface from being damaged in acid. So one of them is just addition of diluted iodine or iodide solution, and the other one is based on adding copper nitrate to fuming nitric acid. And by that, a barrier layer of enlarged cupric nitrate and silver nitrate particles will be formed on along the silver wire. One more method is saturation etching, where researchers used silver nitrate to saturate fuming nitric acid, and in that way the damage of the silver wires was also sort of avoided. However, this approach requires a specific reserve type of acid system. Even though proposed methods did bring some improvements, there are still drawbacks and limitations to them. Mainly wire pitting and also wire thinning still occurs to a certain extent, and that will influence the mechanical test accuracy. Furthermore, introduced artifacts and removal of original failure sites also affects true root cause failure analysis. Another complication which should not be disregarded is accuracy in mixture preparations and also their shelf life. This is an MIP solution to decapsulation of packages which contain silver wires. Namely, we found that the mentioned drawbacks can be overcome by using microwave induced plasma, which comprise hydrogen. As an example here, we show MIP decapsulation of package with specified silver wire and mold compound type. After MIP decapsulation, silver wires, silver ball bonds, aluminum bond pads, and also passivation layer on the die have all been cleanly exposed without artifacts. In comparison, on the image on the left, you can see the same sample after acid decapsulation, which shows severe corrosion damage. And I believe we already have this image in the previous presentation. So another case study I would like to mention is MIP application on system in package. So decapsulation of SIP modules is a tremendous challenge in FA due to their increasing complexity. A wide spectrum of materials and packaging structures can be integrated in a single module, and failure sites like electrical overstress, contamination, or corrosion may appear on any of these components. Now, the capability to expose and preserve all of the components as well as the original failure sites is the key to ensure a high success rate in failure analysis of SIP modules. The module we have here has the size of around 2.5 by 3 centimeters, and as can be seen on the left, module decapsulated by acid has been severely damaged by corrosion, and stack dies also suffered from wire bonded stack dies also suffered from corrosion. Moreover, multiple flip chip CSPs and passive components were simply removed from the substrate by acid etching and left behind only some soldering marks. On the image on the right, halogen-free MIP has been applied to open the entire module, and MIP decapsulation was run fully automatically until the wire bonded stack dies, flip chip CSPs, and passive components were all cleanly exposed without damage. Next FA case study is a surface corrosion. Here we will investigate applicability of MIP in decapsulation of complex 3-layered stacked die IC package, where we deliberately introduced contamination. An additional decap challenge in this package was that it had epoxy refill and it has also undergone ultra-fast testing. The challenge with acid and also CF4 containing plasma method is in this particular FA case study is that contaminant and or the surface of the dye are being etched, and that actually destroys the evidence. Now let's mention how the samples were preparated. Let's start with this failed sample on the left. First, the package was partially decapsulated, and saline contamination was deliberately introduced on the second dye in the stack. Package is then refilled, and refill devices has been exposed to ultra HAST testing. After that, a leakage was verified. Reference sample on the right has undergone the same preparation procedure, but there was no deliberately introduced contamination. Let's discuss results. So after MIP oxygen-only decapsulation has been applied for both of these samples, the reference sample showed no apparent abnormalities on the second dye, and EDX on several locations, also on the surface of the second dye, witnessed that there was no contamination present. Now, after MIP decapsulation of failed sample, it was already with optical microscope obvious that there was this suspicious topography on the second dye. SCM imaging further revealed that there was a thin layer of foreign material present on this location, and EDX analysis on the same location showed traces of sodium and aluminum. Sodium obviously originates from the saline that we introduced, and aluminum possibly occurs due to corrosion of aluminum bond pad. So to conclude, here MIP technology proved its unique capability to preserve original surface corrosion in a complex 3D stack die package. Next failure analysis case is halogen contamination, which is a frequent cause of corrosion-induced bond failure. So acid decapsulation and halogen-containing plasma can introduce foreign halogen, but they can also remove the existing one. So with these two methods, it is actually impossible to tell where the detected contamination comes from. So in this case study, multiple SOT samples from the same batch showed electrical failure, and the device has 2 dyes and 4 ball bonds in total, and bonds are gold aluminum. Several failed samples were decapsulated by acid, and then it was found out that the bond lift was always lifted, that the bond lift was always present on one exact location, while the other 3 bonds were intact. EDX can be performed on this, was performed on this lifted bond, and it showed a growth of intermetallic compound. However, after acid decapsulation, it is not possible to determine the root cause of the IMC growth. To solve this dilemma, MIP was applied to decapsulate failed samples, and the outcome was the same as after acid decapsulation. So again, the bond lift occurred on the exact same location, and the other 3 bonds were intact. TOF SIMS analysis revealed that the chlorine amount on the failed bond was significantly higher than the chlorine amount on the intact bonds on the same sample, and also on the samples from other batches which passed qualifications. Because MIP contains oxygen only, it could not introduce halogen contamination. It is the only logical conclusion is that these abnormally high chlorine levels actually originate from the sample itself.
Violet, to 3 minutes.
Okay, so I will just finish this one. Further investigation, X-ray imaging actually showed that this higher wire loop and unfortunate choice of laser marking location contributed to forming an ion path, which ultimately induced the bond failure. And because I didn't plan the time well, I would like to skip this last case study and just start with the questions, if it's okay.
Sure.
Oh, sorry, well, the summary. So just to conclude, MIP has unique applications in reliability testing, where it provides undisputable results for reliable cool and shear testing, and also for automotive devices which have undergone extensive testing. In failure analysis, MIP gives 100% success rate, which is of crucial importance for field return FA. Thank you.
Thank you, Violetta. Excellent presentation. A couple questions have been entered here. One, what is the sample size that the MIP machine can process?
So the minimum sample is not really determined. So it can be even less than 1 by 1 millimeter. And the maximum sample size is determined by the geometry of sample holder. So the sample holder, which has been developed for decapsulation directly on top of PCBs, can accommodate samples with maximum size of 8.5 by 9 centimeters, and the overall height can go even up to 1.2 centimeters.
Okay. Next question is, you mentioned chlorine in case 2, but what about the other types? What are the other types of corrosion that you mentioned in case study 3 and the case 1? Were you able to determine what they were?
So by case 1 here, so this corrosion here, it was introduced deliberately. So we just applied the saline solution on the second die, and then we found the presence of sodium, and so it is actually deliberately introduced.
Okay, thank you.
Thank you.
Thank you very much.